So for our second panel discussion, we're going to talk about new supply chains. And we're going to feature three innovators, NTT Research, Rapidus, and Edge Cortex, who are all inventing new supply chains. Our panel will be moderated by Jay Goldberg, who is Senior Analyst, Semiconductors and Electronics at Seaport Research. He has previous experience at Deutsche Bank, Peregrine Semiconductor, and Qualcomm. Mr. Goldberg started his career at Coca-Cola in China, and he's also the co-host of the Circuit Podcast, a podcast on the semiconductor industry. I hope you're all signed up for that. So thank you, Jay, for joining us and introducing our panelists as you lead the discussion.
All right, thank you. We stand between you and drinks, I guess, so we're going to be efficient. Thank you for the good introduction. I'm Jay Goldberg. Let's get right into it. I have with me a distinguished panel, and we're going to talk about, I think, loosely speaking, that third helix that we were speaking of earlier, looking at supply chains and the practicalities of bringing this all together. With me is, each of my panelists is going to speak for a few minutes, giving a presentation, and then we'll get into a little bit of Q&A. I have some questions. We'll also take questions from the audience. So first up is Kazuhiro Gomi. Is that right? We go in that order? Okay. From NTT Research, please. Okay.
All right. Good afternoon, everyone. Thank you very much for the intro, Jay. My name is Kazu. I'm the CEO of an organization called NTT Research, which is that, as the name says, that we are doing R&D activities for this company, NTT, used to known as Nippon Telegraph and Telephone Corporations. So a bit of a quick updates or introduction of myself. I've been in Bay Area for the last 6 years, basically running this organization, NTT Research. But prior to that, I was running NTT's North America business out of New York. I was the CEO of NTT America and running data centers and global networks and so on. So that's my quick background. And a bit of thing is that I'm also a board member of Japan Society in Northern California. So I have quite a few board member colleagues in this room. Okay, with that, let me just switching a gear, just to show you a few slides about this thing, next generation semiconductor, photonics integrated circuit. Well, today's topic so far is semiconductor. And when you talk about semiconductor, most of the technology is based upon silicon. Yeah, here's the thing. You know that the Moore's law has been kind of driving that this innovations of semiconductor technologies, and which led to the information technologies and digital technologies and so on and so forth. This was the importance, very, very important thing. But probably many people have heard about that, the limitation of the Moore's law, the death of Moore's law. Basically, we got to the very close to that limitation that you cannot put any more transistors on the silicon wafer. So that is a problem. But don't get me wrong, there are definitely a lot of interesting technology, like some people talked about the 3D processing and so on. So there's still a bit of areas to improve, to shove in more transistors on the wafer. However, actually, at the end of the day, one of the biggest problem of the silicon or the today's proliferations of the computation requirement is this one. CPU, basically the CPU clock speed has been stuck in the 5 gigahertz over the last maybe 10 years. And then we don't see much of a room to go beyond. And the reason is when the CPU clock speed goes beyond this, it starts melting. It generates too much heat. So you cannot put more computation power on a chip. So, but on the other hand, as you know, that the AI is such a big theme now, and everybody needs that more computation power. So what do? So we have to kind of shove in more servers, more data centers, and then more energies. And by the time you know it, a couple of days ago, State of Union, one of the stuff that Trump mentioned was the AI data centers is rising. Basically, one of the problem of that the rising utility power cost. And I don't know how true that is, but it is true that we are running into a major problem. So this is, I mentioned AI dominating the world, and more computation power is required while managing heat. And then AI requires high-speed data transfer between the memories and processors and between the processors and so on. And the problem, just to dissect the problem of this energy, is that computation itself and also this transmission of the data between the memory and the processors. AI requires a lot of it. So this is the problem. And electronics, which is the core of today's technology, requires a lot of energy when it comes to the high-speed data transmissions, and also if the distance gets bigger between point A to point B. The distance, what I'm talking about, is not the kilometer. It's just about 10 centimeter or 20 centimeter. That distance increase creates a huge power hug just for that. So with that old background, what do? So then many speakers, Nishikawa-san mentioned a little bit about photonics electronics integrations. So that we believe, from NTT's perspective, photonics is the answer to it. So photonics by itself, by its nature, doesn't require much of energies for the distance and then the higher speed data transmissions. And also, I'll talk a little bit about that, but photonics has, by nature, really interesting features that you can do the computation required for AI by itself. So that's the importance of that, and NTT has a roadmaps for this photonics and electronics convergences. We started out this journey in 2020, about 2020, and we have a roadmap towards 2030. But basically, I'm kind of spending too much time, so I'll skip a little bit, but we have roadmaps to basically implement that photonics side, using the photonics circuits to connect different pieces of the IT infrastructure between the board in the servers, between the chips on the board, and within the chip, between the die on the chip. So those are the technology we're looking at, and we have created this initiative called ION, Integrated Optical and Wireless Network. So we are at this stage, we just started calendar year 2026, and we are on track to ship the first commercial based, that kind of sample base, the chip by the end of this year. And then we are looking at by 2028, we are doing a little more further that the integrated photonic circuits on the chip. And then lastly, so we are in research. So I wanted to kind of talk a little bit about, I mentioned that photonics is good at doing the AI computations, and this is one of the examples of that. This is the newest of our researchers' results. We published on Nature a couple months ago. We did the machine learning done by the photonic circuit. And then in this case, this is that kind of very mimic easy AI, so handwritten recognitions. So in this case, that the handwritten number recognition can be done on this just a photonic circuit. No GPU, no digital circuit whatsoever. You can do that. And what's cool about is that if you see that there's a light on the top, if you change the light, you can fine-tune this machine learning. And this case is number recognition. You can actually run, say, alphabet handwritten recognitions using this circuit. And then this is all can be done in photonics. And then the required energy is just a fraction of what you need for today's AI. So I should stop here, but that's my kind of message. Thanks for listening.
So Hiro did an admirable job of condensing an incredibly important topic, very complicated, but really, really vital to networking and to AI into a very short amount of time. The next topic is Henry Richards. Henri, please go ahead. He's going to talk about Rapidus and how we actually build all these things.
So good afternoon. My name is Henri Richard. I have the privilege of being the president of Rapidus Design Solution, which is the US arm of Rapidus Corporation. I feel like you already know a lot about us because Nishikawa-san spoke about the creation of the projects. You know I'm old. You know my salary is lower than the industry. So, I'm not sure what I should be talking about. But anyhow, I'm going to pass on this since you've already seen this slide. And I'm going to show you a little bit of eye candy, which is, this is the fab. And I want you to imagine that just in September 2023, this was a big field of dust. And now you have this world leading edge fab at 2 nanometer, which is the size of 11 football fields, producing test wafers. And we're very proud of that, and that's why the name of the company is Rapidus. This is an absolute demonstration of the strength of the core values of Japan: discipline, commitment, innovation. And we were talking about, bringing talent. I can tell you we have no challenge in bringing talent because everyone looks at this project not only as a wonderful industrial project, but as a national pride. And I'm not Japanese, but I'm very proud to be part of this adventure. You can think of us as one of four: Intel, Samsung, TSMC, of course, and Rapidus. But that's not the right way to think. We're one of two in the sense that we're the only two, TSMC and us, that don't have captive internal demand. And, in fact, we're one of one. I'm going to pass the video. We're one of one because this is the first semiconductor advanced fab in the world that is using a single wafer processing process. It's a concept that was written up by our CEO, Koeki-san, over 20 years ago. And the reason it's important, without going into the details, because I'm not sure what's the level of proficiency in semiconductor manufacturing of this audience, but think of it as instead of manufacturing batches of wafers, 25 at a time, we have created a fab that can process them one at a time and measure one at a time what's happening on the wafer. When you inject that amount of new data into an AI engine, that allows you to have a turnaround time that is half of the industry. So if you're a chip designer in this new age of AI, with a lot of variability in your chips, a lot of new ideas, and you give us a file, we can give you a chip in half the time of the rest of the industry. That's the name of the company. Thank you.
Next, next we'll have Sakya Gupta, who's going to pull it all together and show us what we're going to build with all these interesting chips.
Thank you to the organizers for having me. Unlike my fellow panelists who need no introduction, I'm glad that I'm getting the opportunity to present who we are as Edge Cortex. We probably do need introduction. I would say, before I kind of start and introduce the company a little bit and what we are doing, I think we are probably among the new age Japanese companies, young in age, but rich in experience. In a manner, we are a product of, I would say, the Transpacific collaboration. We are at the intersection of, in a manner, what my fellow panelists are doing here. So like you have Rapidus on the manufacturing capacity foundry side, and you have entity research on the network layer. You can think of us as Edge Cortex. We're trying to build the intelligence layer that has to be efficient, it has to be scalable, it has to be interoperable. And we are really focusing on the part of the market that we call edge. Think of it as the rest of X of data center, where 75% of the world's enterprise data today is being generated and processed. It's really constrained by size, weight, power. So fundamentally, you not only need efficient semiconductors, but you really need to rethink the intersection between software, architecture, and the semiconductor technology. And that's a tall order, but that's really what we are going after as a company. We are Japan-founded. Our architecture, our NPU technology, the silicon, the core brain of what we put into our semiconductors is from Japan. Our core processor and software is produced in Japan, designed in Japan. But we also use the mature and advanced node manufacturing today in Taiwan, and we believe we have the roadmap towards bring that to Japan in the future through Kumamoto, and then probably in the future through friends like Rapidus as well. So in a manner, that's the reason I said that really am being at the intersection of the Trans-Pacific collaboration. We also do the product developments and deployments across US and Japan. And in a manner, if you think about today from semiconductor technology, as Nishikawa-san also mentioned in his presentation, it's not just about the core capabilities of the semiconductors, but if you think about economic security or national security, you got to also think about applications that may be mission critical, dual usage. So in a manner, we as a company, we are not only focusing on applications on the commercial side, on the industrial side, or robotics side, but we are also working with organizations like the Defense Innovation Unit, being one of the first Japanese companies to be selected by the DIU. I see there are fellow DIU members here in the audience, to essentially use our silicon and technology to apply in mission-critical areas as well. I would also say that building semiconductors today, and especially designing semiconductors, so we as a fabless semiconductor technology company, it's not just about the semiconductor or the architecture itself. It's really the ecosystem. It takes a village and many, many countries, so to speak, to build semiconductors from architecture, from design, from the software that will really realize the semiconductor, and then bringing that downstream to the end customer, which is really the proof of what we are producing as the technology. On the left-hand side, you have the traditional semiconductor value chain. Clearly, Rapidus would be amongst the new age fabs and manufacturing capacities that are coming up steadily here. We as a company, we are essentially on the fabless side. So we are really focusing on the design aspect where the chips needs to be extremely energy efficient and scale for AI processing, which is the dominant kind of user, so to speak, of semiconductors today. It also requires building a very strong ecosystem. And as Nishikawa-san was mentioning, we started in 2019, so we are still a fairly young company. And then over the last 6 or 7 years, we have clearly seen a steady growth in the overall ecosystem in Japan. But then when we started, we really started with Japan as our core home, but then global first, or in a manner, Trans-Pacific collaborations from day one. And that's reflective of the ecosystem of partners, which includes the foundries. Of course, we're working with TSMC, but it also includes the rest of the supply chain, EDA, IP, system providers across Taiwan, across US, Japan, and other friendly countries, including Europe. And then, of course, the government bodies. If you're building semiconductor and designing today, it goes a long way to be able to, of course, bring that to market, but also through support, through subsidies and other programs that the Japan government has. So we have been fortunate to be supported in our next generation programs through METI, NEDO. We do work on the dual usage side, where it's mission critical system with our partners in the US, including space applications. If you think about space, that's really the final frontier of an edge computing. You don't get any more critical in terms of requiring constraints that you need to satisfy to run AI. And so we are focusing with NASA's collaboration today on the space side, including companies like iSpace in Japan for their moon missions. Finally, touching a little bit about the technology itself, and I was really kind of encouraged by the slide I saw on Kato-san's slide when he talked about software-defined vehicles. If you recall that slide, it had two axes, power efficiency on the x-axis, and the vertical axis, if I recall it, was performance. What we have focused on is two axes. One is performance. So fundamentally, you've got to grow your performance, but you want to reduce your power consumption in a manner that intersects with the top right quadrant that was there in Kato-san's image, where the focus really is, as the demand for semiconductor grows, driven by the explosive growth of AI, energy is the fundamental bottleneck. You really need to solve the power challenge. And as NTT Research mentioned, you are going to need photonics technology or others to essentially drive high-speed communication. We are focusing on the semiconductor piece and the architecture and software required to essentially drive power efficiency for that AI processor directly at the edge. Today, we focus on monolithic chips. What you see here, what we sell to our customers globally today, is produced by, with our friends in Taiwan with TSMC on 12 nanometers. But then clearly there is path to also produce that in the future in JASM, we believe. But that's focused on monolithic. Where the world is moving today is disaggregation. Think about essentially a paradigm shift in semiconductors where you're driving it for interoperability, system scalability, which is the next frontier. We call this chiplets, disaggregating dies into different components, where it enables us to get over some of the hurdles that Gomi-san mentioned, basically Moore's law slowing down. So moving from the traditional transistor scaling to system scaling is what we can do with chiplets. And I think that's an area that we're focusing on. Again, we have the guidance of Mehdi and Nedo to essentially bring the intersection of AI and network communications. And that drives across the gamut of different applications. So ultimately, the proof of what one creates is at the intersection of how do you realize that in applications, in real-world deployments. That spans across defense, aerospace, robotics, AI, RAN. That's really the intersection of next-generation post-5G world, where AI and telecommunications really needs to come together. And that's been also a critical focus for us. Last but not the least, I would say today we are in this era of sovereign AI, as we have seen, and we have the pleasure of Professor Ota being in the audience as well. That's the book, The Geopolitics of Semiconductors. And we have clearly seen in the last few years there has been a dramatic influx of investments across different government bodies realizing the importance of semiconductors, and I would argue in a manner driven by the growth of AI, that now is focusing on manufacturing capacity, R&D, attracting talent through subsidies, loans, and investments. Last but not the least, I would say in order for the semiconductor collaboration across the Transpacific to be successful, in my opinion, is not just about Japan playing a critical role on manufacturing capacity, but it's also important for Japan to focus on architectures, fabless side, the design ecosystem. That's going to be the lifeline of any foundry that comes up. Looking forward to panel discussion. Thank you.
So I'm just a lowly analyst. I'm going to have to ask a naive question. The theme of this conference is international cross-border cooperation, Trans-Pacific collaboration. Why do we need that? Why can't we all just do our own thing? Right?
Well, there are many, many reasons at the end of the day, but I think that the biggest one is the talent, and then the exchanging the ideas and diversity. I truly believe that's the most important part.
Well, you just talked about it. There's a paradigm shift in the industry coming with chiplets. You know, in the past, foundries didn't talk to each other. We're not necessarily enemies, but we're not necessarily friendly either. However, when a customer will have on the same chiplet products from global foundries, TSMC, Intel, potentially Samsung and Rapidus will have to collaborate. So by nature of the chiplet revolution, this business which was very monolithic in the relationship between customers and foundry, is going to become much more polygamic.
And just to add to that, like if you think about chiplets itself, the whole idea is today we talk about supply chains, but I would say it's a misnomer. In a world that is largely becoming Transpacific and collaborative, if you think about a triangle between Japan, US, and Taiwan, chiplets in a manner makes it into a supply cycle, I would argue, where you don't have any single point of failure, and it's not just about manufacturing capacity in one place, design in another place, architecture in another place, but it's really a holistic combination where each of those components feeds into each other. And I think that makes a big difference today.
Very interesting. Can we talk a little bit more about the supply chain? That's the theme of this panel, actually, is supply chains. What else are you seeing? What are you two seeing that is sort of changing rapidly in the supply chain? What do you think is most interesting?
So I think enough has been, in a way, many things has been said, but yeah, at the end of the day, we learned the lesson through the COVID, and then now supply chain disruptions and so on. Then so too much one concentrations on one area is a problem. Therefore, we are diversifying all that fab locations and so on. But the behind the scene also, that where the wafers are created and who can create those wafers and supply the wafer itself to that processing unit. So I think that there are many aspects of it, and then a little bit addition to that. So when you look at photonics, electric convergences, and so on, that we have to kind of start looking at different material as well beyond the silicon. Yeah. So that's still kind of on the way, but we definitely start looking at it. What's the what could be the problem for the newer material, newer technologies.
So I think we need to be very sober about the fact that we are at a moment in time where we have some antagonistic forces at play. On the one hand, we've all heard that semiconductor leadership is a matter of national security. So everybody wants to have control over their national security. And on the other hand, we hear that for customers to execute their project, they're going to need more collaboration around the world. I'm not sure which tug-of-war side is going to win. We certainly are proponents of collaboration, but governments change, and it's been a difficult environment for customers to navigate, to say the least. And so we have the benefit of not being in production until 2027, so I've got time to look at what's happening. But I do believe that this is both the most exciting time that I've ever seen in my career in semiconductor, but also one of the most troubling times if you want to be a little bit more down to earth.
That's the one time you're going to say you're glad you're not open yet. That's right.
And if I may add to that, I think just stepping aside from the geopolitics on the technology, going back to the chiplets topic, because that, in my opinion, that's really changing what supply chain used to be. There is going to be very less amount of single points of failure or concentration. And in a manner, it's short-circuiting the journey from lab to fab, where you have the full stack across packaging, advanced packaging, from the wafer, advanced packaging, materials, architectures, all coming together, where you do not require a tremendous amount of time to journey from the original design to the actual fab out. The second is, I think we as a company, we are also looking at cross-foundry collaborations in the sense, I think chiplets really enables that. So today, a lot of the chiplets has been homogeneous, where, for example, we are producing with TSMC, with the critical technology of die-to-die interconnect that we have, alongside AI processors, there's no reason why we cannot talk effectively with somebody like Rapidus. And I think that will become an enabler in the future. So today, let's say you're at 6 nanometer, 3 nanometer on dies on TSMC, you may want to talk to a different die, which is on 2 nanometer from Rapidus, which may be doing a very different part of the computation process. Could be I/O, could be memory. And that changes the overall supply chain perspective.
So, Andre, you've opened the door. You used the word politics. That's sort of the elephant in the room. I think we all know it's complicated, and there's all kinds of things we don't may not be so happy with in the world right now. Let me turn the question around and ask each one of you, if you were speaking to leaders today, what is one policy change you would like to see? And you can pick whichever country you want.
Well, I think that we have a larger area of the world, a third of the world GDP, namely Europe, that has no production, and yet detains the most powerful single point of failure of the entire industry, namely ASML. So if I had to give an advice to politicians is, please stay nice to the Europeans. Because if you want to build a new fab in Hokkaido, in Kumamoto, in Arizona, or anywhere in the world, and you piss off the Europeans, we're in deep trouble.
Anybody else want to? You got any policies you'd like to see from your government, this government, any government? No, I don't mean
not right now.
Okay. All right, let me take pause and see. Do we have any questions from the audience? There's a hand raised right here.
There is also a very loud voice here.
Wow.
Okay, so this actually goes to Revitalize. So I'm Glenn from Fujitsu. Look forward to our new Monaco chip rolling off your line sometime in the future, maybe. Yes, indeed, don't worry about it.
It's a secret.
It's totally now publicly. But my question to you is, so yesterday I was given the announcement that the Japanese government has made an amazing, let's say, investment in your company. And I wanted to know if you could characterize how that may impact your roadmap moving forward, your timeline for 2 nanometer. What's going to happen because of that?
Yeah, so maybe for everybody that may not have been so much tuned into us as you are, there was an announcement yesterday, Japan time, of large investment from both the Japanese government and 32 private companies or public companies in Japan into Rapidus. This goes back to what I was saying about the national pride and the amount of support that we have in Japan. This investment was planned. It's not new. It's part of the roadmap. And, as I think Nishikawa-san was saying, the story of Rapidus today is so far so good. On schedule, on budget, and a lot of customers hoping for us to execute as we promised.
So just looking at the panel here, I don't want to add it up, but there's a significant amount of experience, years of experience on the stage right now. You all have been around the industry for a long time. As much as things seem like they're changing rapidly and everything's a new thing every day, we've all been doing this a long time. What are things from your personal history that you've seen or you've heard about that you think are relevant today that we need to remember? What lessons from history do we have?
I can go first.
Please.
The youngest in the audience, or in the panel. So I think one of the lessons that we started with has been, especially today, the topic is semiconductors and supply chain. But hardware and semiconductors without software is basically a research project. And software is really the elephant in the room, and I think there has to be a concentrated effort while the fabs critically grow, the semiconductor technology grows, the software and the architectures and the fabless design has to also grow, in my opinion, equally fast or faster, so that you can drive or sustain that manufacturing capacity that you're building. So that's been our experience.
To me, being exposed a lot to, of course, Asia and Europe, besides the US, I would advise everyone to not forget the disruptor dilemma. I see a vast difference of grasp of how much AI is changing our world when I talk to my European friends and even my Asian friends, with all due respect. And I think that the amount of disruption to the existing order that AI will bring to not only our industry, but the entire world, is largely underestimated. And so if there's something to learn from the past is we've seen these waves of disruptor technology, and I don't think we've seen anything even remotely as big as what we're seeing right now.
So maybe AI will write all your software and solve the software problem.
Yeah, absolutely. AI, we cannot ignore that. AI is very, very important for many different ways. But back to your original questions, I think that many has been said that Japan used to have a pretty dominant positions in semiconductor world, and then we basically slipped down from there. I think there are many, many lessons why that happens, and many, many books been written. But at the end of the day, well, we were late, or we didn't play a very good role in that the systems, chips, and then processors. At the end of the memory, Japan was good at memories, but not so much on processors. So. And then at that point, that the processor was where the value was. So I think we had to all think about, it's kind of very basic business rules. What kind of technology or the systems or solution that has the core value to the client, to the market? I think we have to really always think about it. That's I would like to say that that's the lesson. And another thing maybe is that the ecosystem, that's the word many times has been used. How to make the friends and then ecosystem, and then you have to be in the winning team at the end of the day.
And if I may just add to that, I think in our experience as building a company, especially to hopefully the entrepreneurs in the room, I think like ecosystem is not just about the partners and the supply chain, it's also about the people who build the company itself. And our experience has been, while we're in Japan, from day one, got to have a global first or global mindset. And that's reflecting the team that you build as well. For example, we are headquartered in Japan. 30% of our workforce, engineering workforce, is Japanese. 70% is from rest of the world, 15 different countries, nationalities, almost a Silicon Valley style operations. And I think that's really the collaborative model of whether it's the supply chain or it's the companies that you build today in the semiconductor and AI era.
I think that's the answer to my first question, right? Because you're Japanese and you live here. You're not Japanese, you work for a Japanese company, you live in Japan.
I'm not Japanese, right? And I live in Japan.
So we've just answered that first question about why collaboration matters. Let me just take one last poll. Anyone, any questions from the audience? Yes, sir. So let me repeat your question so everyone can hear. I'm going to elide over the troublesome history of the memory industry and the U.S.-Japan relationship and skip right to the question of today, which is, we have a memory shortage. It's critical in a lot of areas. There's not enough memory chips in the world. What are we going to do to address it? How do we navigate around that?
I don't have a very good answer, but. Yeah, but it's kind of interesting that I'm kind of dodging your question a little bit, but so memory, kind of value of the memory went down at one point, but right now, as you said, that the value of memory is kind of coming back up. So those waves or the pendulum of the swing of pendulum is really happening. So I think it is from the industrial people's point of view. How do you foresee that pendulum, where that's swinging from one direction to another? I think that this memory story, when I heard about it, that's the first thing I thought.
I have a prediction for you. You know, first, of course, we are the most capital-intensive industry in the world, and so that makes it very difficult to plan ahead of time because it's very expensive when you make a mistake. However, I think John mentioned that the biggest wall that's in front of us is that we are a runaway train in power consumption, And I promise you that there is not enough electricity in the world to power the forthcoming earnings announced by NVIDIA, AMD, Broadcom, Marvell all together. Somebody is going to miss a quarter. And it just takes one of those big guys to have a little problem, and your memory pricing will be a lot better.
Okay, we're running out of time. Let me just do one last quick question, which is we're on a college campus. Go Bears! There are a lot of students, especially in the back. What is one piece of advice or one career field you think students should go into today, right? So that they can sort of maximize the arc of their careers. They're starting out today. What should they go into?
There's a lot being said about the computer science degrees, right?
Yeah.
Recently, so that kind of makes some people nervous, perhaps. But at the end of the day, I think I'm back to this AI issue, which may not be the main theme of this conference today, but I think it's the matter of how you embrace AI. If you can embrace AI correctly, you can be the winning case. And if not, I think you're in a vicious cycle from there. So just be aware of what's going on there.
I'll give you a career advice. Always put yourself in a position to fire your boss.
Well, from that anecdote, I will say that I think clearly the discussion today is centered around semiconductors, and while there is fantastic fabs and technologies coming out on the manufacturing and packaging side, we need more designers, clearly. And I think that would be the area. And if you're focusing on design, especially on kind of semiconductors for AI, focus on memory and focus on I/O. How do you move data faster? And how do you store that data very, very quick, kind of in a high capacity and very efficiently and in a power efficient manner?
Analog, true, close to my heart. All right, gentlemen, thank you very much. I really appreciate this.